In the previous section, we looked at projecting a vector onto another vector. Here we're going to look at projecting a vector onto a subspace. And the idea is very similar. If you think about when we projected, we got this vector. And notice that the y was equal to the y hat plus z, where this is z, y hat, and y. And basically, another way to think of this is that you split the y up into two components that are perpendicular. So that's what this first part is talking about, that you break it up into things that are orthogonal and the orthogonal complement, which we talked about, this W perp. This theorem, this orthogonal decomposition, is that idea that you can decompose a vector into a vector from W and a vector from the W complement. This formula for finding the projection, notice this piece should look very familiar. It is the same as if you're projecting onto a vector. Because we're projecting onto a subspace, we just have as many of these as we need, which is dependent on the size of W. So let's look at this first exercise. I want to verify first that U1 and U2 is orthogonal. So let's do that first. So U1 dot U2 is -1 plus 1 plus 0, so that works. And then we want to find the orthogonal projection of y onto the span of these two vectors. So we're going to think of W as the span of U1, U2. So we know that the orthogonal projection is y dot U1 over U1 dot U1 times U1 plus y dot U2 over U2 dot U2 times U2. Y dotted with U1 is -1 plus 4 plus 0. U dotted with itself is 1 plus 1. Y dot U2 is 1 plus 4 plus 0. And U dotted with itself is 1 plus 1. Simplifying, we get 3 halves times 1, 1, 0 plus 5 halves times -1, 1, 0. So 3 halves minus 5 halves, and then 3 halves plus 5 halves, and then 0. So I get -1, 4, 0. So this is the orthogonal projection onto that subspace spanned by U1 and U2. Exercise 2 is mathematically asking you to do the same thing, but the words are slightly different. So we are going to verify that U1 and U2 are orthogonal. Then it says write y as the sum of a vector in W, that would be the y hat, plus a vector orthogonal to W, so plus z. So that is just asking us to decompose it. So I'm going to first find y hat, and then I'll find z. So I guess first I need to verify that U1, U2 is orthogonal. So I get 5 plus 3 minus 8 is 0, so that works. And then y hat is going to be y dot U1, or U1 dot U1 times U1, plus y dot U2 over U2 dot U2 times U2. Y dotted with U1 is 1 plus 9 minus 10 over, I don't know, it doesn't even matter because that's 0. I'm just going to put some number times U. All right, y dotted with U2 is 5 plus 3 plus 20. And U2 dotted with itself is 25 plus 1 plus 16. So again, this piece is 0, which is why I didn't finish that one. I have 28 over 42 So we have 2/3 times 5/1/4, which gives me 10/3, 2/3, 8/3. So there's my orthogonal projection. Now to find z, it's y minus y hat. So y is 1, 3, 5 minus 10/3, 2/3, 8/3. So I have a negative 7/3, 7/3, 7/3. So what this tells me is that my y can be broken up, so 1, 3, 5 can be decomposed into y hat, the 10/3, 2/3, 8/3, plus negative 7/3, 7/3, 7/3. And these two are orthogonal. So let's just check. So z dot y hat would be negative 70/9 plus 14/9 plus 56/9. And that does equal 0. So check. So this is really, really, really important. So what it's saying is that the orthogonal projection is unique in W, so there's only one of them, and it is the closest vector to Y. So if you're trying to find a best approximation, you want to find the closest vector. So when you find a line of best fit, you're finding the closest line that fits the data, or the best. This is just saying it another way, the best approximation theorem. So we have W is some subspace, Y is a vector in Rn that is probably not in W, and Y hat is the projection onto that subspace. This just tells you it is the closest. So the length, the distance between Y and Y hat is smaller than the distance between Y and any other vector in W. So Y hat is the closest vector to Y that is in W. So because it's the closest, we call it the best approximation. In exercise 3, we want to find the closest point to Y. So I'll try to draw this. So if this is W and Y is something out of, not in W, doesn't lay flat in W, I want to find the closest vector to that. Well, the closest vector that is in W will be the orthogonal projection. In order to use the formulas that we have, I need to make sure that V1 and V2 are orthogonal. So let me check that first. So V1 dot V2, I have 3 minus 1 minus 1 minus 1, which is 0, so good. And so now I'm just going to try to find Y hat. So Y hat is Y dot V1 over V1 dot V1. So let's look at Y dot V1. I'll have 9 plus 1 minus 5 plus 1. V1 dotted with itself is 9 plus 1 plus 1 plus 1 times V1 plus Y dot V2. So I have 3 minus 1 plus 5 minus 1 over 1 plus 1 plus 1 plus 1. Nine, 10, 5, 6. And here we have 3 plus 5 is 8, and then 6 over 4. I have 1.5, 0.5, negative 0.5, 0.5, plus 1.5, adding them together, I have 3, negative 1, 1, negative 1. So this is my orthogonal projection of Y onto the subspace generated by V1 and V2, and that is the closest point. It then says, what is the distance between y and w? So I'm trying to, this is y, this is my z. The z is the distance between them. So I could do a variety of different things. I could use Pythagorean theorem, because I know that the norm of y is equal to the norm of y hat, squared, plus the norm of z squared. So let's try it that way. So the norm of y is the square root of y dotted with itself. So that's 9 plus 1 plus 25 plus 1 squared equals the dot product with y hat with itself. So I have 9 plus 1 plus 1 plus 1 plus norm of z squared. So I have 36 is equal to 12 plus norm of z squared. So the norm of z squared is 24. So square root of 24 is the length of z. This final theorem shows a simplification of finding the projection onto a subspace when you have an orthonormal basis. So thinking about that, the original formula, the y hat equals y dot u1 over u1 dot u1 plus y dot u2 dot u2. So it keeps going, but if it's an orthonormal basis, we know that this is 1, because we know that the vectors dotted with themselves are 1. So that's why all the denominators go away on this formula. And so this tells me the projection. So we looked last time at how to form the U. The U is just the columns from your orthonormal basis. And we saw last time that U transpose U is equal to the identity. But U times U transpose times Y gives you the projection. So in this example, we have U1 and U2. We should verify somehow that they are orthonormal before we use that theorem 10. And that's what part A is asking us to do. So let U be the columns, the orthonormal columns, and I want to compute U transpose U. So U transpose means I'm going to have 2/3, 1/3, 2/3, and negative 2/3, 2/3, 1/3. That's the transpose, so instead of the columns, they're rows. And then 2/3, 1/3, 2/3, negative 2/3, 2/3, 1/3. And then multiplying. So first one is our first entry. Maybe I should look at the size. So this is a 2x3, this is a 3x2, so I should have a 2x2. So this is 4/9 plus 1/9 plus 4/9, which is equal to 1. And if I keep going, I'd have negative 4/9 plus 2/9 plus 2/9, that is 0. Again, is this one times this one. I get 4/9 plus 4/9 plus 1/9, which is equal to 1. So this is equal to the identity, a 2x2 identity. What that tells me, because when you do U transpose times U, that does tell me that those are orthonormal columns. So to compute the projection, I can do U transpose times my Y. So just writing out my U. And here this is a 3x2 and a 2x3. So the product of those two would be a 3x3. But then I want to multiply by my vector, 4, 8, 1, which is a 3x1. So again, all these inner dimensions have to match, and they do. So just something computationally, like if these were larger, this would make a big difference. You would want to multiply these two first because there's less flops. which are like additions and multiplications, and then you'd multiply by this last. So that's what I'm going to do, just to save me computing time. So this is a 2 by 3 and a 3 by 1, so my outcome is going to be a 2 by 1. I have 8/3 plus 8/3 plus 2/3, and negative 8/3 plus 8/3 plus 1/3. So 8/3, 10, 18/3, and then 1/3. This is a 3 by 2 and a 2 by 1. My outcome will be a 3 by 1. Multiplying these out, I have 2/3 times 6, so that's 4, minus 2/9, and then I get 2 minus 2/9, and then I have 4 plus 2/9. So this is my orthogonal projection.